Welcome back. Today, in this explainer, we are diving right into circles, circumference, area, and volume. We're going to bridge that gap between simple 2D shapes and complex 3D objects, locking in that grade 8 geometry foundation. Let's get right to it.
So, here's our roadmap for today. We'll kick things off with circle vocabulary and angles, move into arcs and circumference, then tackle area and sector area. After that, we're jumping into the volume of 3D shapes, uncovering some wild visual deception in geometry, and finishing up with a recap and a transfer question.
All right, Section 1, Circle Vocabulary and Angles. We're starting out completely flat here, covering the fundamental properties of circles to build our geometric foundation.
Let's see how this actually builds. The radius and diameter are literally the basic building blocks we need to measure any circle. The radius, which we usually just call r, is the distance from the exact center right out to the edge. And hey, if you go all the way across the circle, straight through that center point, you get the diameter. It's exactly twice the radius, so d equals 2r. Simple enough, right?
But now look at what happens when you shift things around. Notice how just moving the vertex completely changes the angle's relationship to the circle. We have a central angle, where the vertex sits directly at the center of the circle, formed by two radii. But if you take that vertex and pull it all the way back so it rests perfectly on the edge, boom, you've got an inscribed angle. Grasping these relationships is absolutely crucial for understanding how circles operate in a larger geometric system. Moving right along to Section 2, Arcs and Circumference. Stepping up from just points and angles, let's wrap a one-dimensional line completely around our shape to measure the perimeter.
So the really cool thing here is that the distance around any circle is always just a little over 3 times its diameter. And we have pi to thank for that. We call this perimeter the circumference. The formula? Well, c equals 2 times pi times the radius. And since we just established that 2 times the radius gives us the diameter, we can also just say c equals pi times the diameter. It's a real game changer.
Okay, let's actually test that out right now. I want you to think about this for a second using the formula we just looked at. If a circular fire pit has a diameter of 5.5 feet, what's its circumference? Go ahead and take a brief pause to work it out.
Got it? The immediate reasoning here is super straightforward. By simply identifying the diameter as 5.5 feet and multiplying it by our trusty approximation for pi, 3.14, we find the circumference is exactly 17.27 feet. That's all there is to it.
On to Section 3, Area and Sector Area. Now let's expand from a 1D line out into actual 2D space and figure out how much flat surface a circle really covers.
To find the total area, we square the radius and multiply it by pi. This measures the entire flat region without any gaps at all. But a quick warning here. Squaring the radius means multiplying it by itself, r times r. It does not mean multiplying it by 2. Oh man, that is a very common trap, so definitely watch out for it. But what if we don't want the whole circle? Imagine an automatic lawn sprinkler that only rotates, say, 30 degrees. That specific slice of the circle is what we call a sector. Finding the area of a sector really just means finding what fraction of the whole circle you're dealing with and then multiplying that fraction by the total area.
Which brings us to our second pause check. Take a quick breather and think about how you'd calculate just a fraction of that total area. Let's say our sprinkler sprays out 20 feet, so there's your radius, and it only rotates 30 degrees out of a possible 360. Exactly what is the area of the grass it waters?
The logic here clicks right into place. You take that 30-degree angle, put it over 360 degrees, and you quickly see you're dealing with exactly 1/12 of the circle. You could also convert that to radians, which gives you pi over 6. Then, just plug that 20-foot radius into the area formula, take your fraction of it, and boom, you get roughly 104.72 square feet of watered grass.
All right, Section 4, Volume of 3D Shapes. This is where we explode outward into the third dimension, seeing exactly how these flat circles form the bases of physical objects.
I absolutely love looking at how these formulas logically build on one another. The cylinder formula, it literally just takes our 2D circle area, pi r squared, and stacks it up by a height h. It's just area times height. Then, brilliantly, if you want the volume of a cone with that exact same base and height, it's exactly 1/3 the volume of that cylinder. And finally, the sphere. It's perfectly symmetrical in every single direction, so it uses the radius cubed in its formula, 4/3 pi r cubed. See? These aren't just random letters. They logically build right on top of each other.
Now for Section 5, Visual Deception in Geometry. You might be wondering why we even need all these exact algebraic formulas when we can just look at a shape. Well, because our eyes can be easily fooled. And this classic illusion perfectly proves why we have to trust mathematical formulas over our own eyes. Think about this. If you cut an 8 by 8 square, which obviously has an area of 64, into 4 specific polygons, you can rearrange them so they appear to form a 5 by 13 right triangle. But wait a second, the math totally doesn't add up. 5 times 13 divided by 2 is 32.5. But if you mirror it to make a rectangle, it's 65. Wait, no way. We just magically gained the full unit of area? How? Well, because the new shape isn't actually a triangle at all. The slopes of the pieces forming that so-called straight edge are actually -2/5 and -3/8. They literally don't match. This optical illusion hides a tiny, completely invisible gap equal to exactly 1 square unit. Crazy, right?
Finally, we've made it to Section 6, Recap and Transfer Question. Let's pull all of these dimensions back together to really lock in everything we've covered today.
So, the absolute biggest takeaway here is how spatial reasoning scaffolds logically from a simple radius all the way up to a 3D sphere. We started with flat lengths, wrapped them up into 1D perimeters, filled those M as 2D areas, and then pushed those areas straight up into 3D volumes. It's like a giant, beautiful puzzle.
Now, before we wrap up, I want you to apply what we learned about that cylinder formula to solve a brand new scenario. Here's your transfer question. If you have a cylinder and you double the length of its radius, exactly how does that affect its total volume? Really think about what happens when you square a radius that has just been doubled. The math tells us it won't just double the volume, it actually quadruples it, because, you guessed it, 2 squared is 4.
Let that provocative thought sink in for a bit. Because geometry, you see, isn't just a bunch of stuff on paper. It's the actual mathematical blueprint of the world around us. Next time you see a circular object, remember the hidden mathematics structuring its very existence. Thanks so much for joining me on this explainer, and keep questioning what you see.